So, today's workshop is going to work in the following way. First of all, we will solve the exam. That way, you can see how it's done. I know the solutions are already on Canvas, but I find it way better if you can follow the process with me as I solve them, in opposition to just having the solution there splashed. So we're going to be doing that first. And second, I will show you how to calculate integrals of revolution solids, which I figured out yesterday thanks to one of your colleagues, and I found it incredibly interesting. Also relevant for the course. So, for exercise 1, we have a rectangle, base x, height y. And it says the width increases at 4 meters per second. First piece of data. Second, the area is constant. From the area is constant, we have y is 20 over x. Because the area is 20. And we want to find how fast does the height decrease. So let's see. If we derivate here, that thing over there, times 4. So we apply our piece of data number 3, and so the decrease ratio of y is minus 20 times 4 divided by 2 squared, which is also 4. So the height decreases at minus 20 meters per second. Now, questions about this first exercise? Yx squared, because you're derivating 20 over x. The derivative of 1 over x is minus 1 over x squared. Obviously, if you multiply this by 20, you get a 20 up there. So without further ado, let's move into the next one. I deleted the title of the exam accidentally. Let's just hope nothing happens. Okay, nothing happens. So exercise 2. We have f of x equal x squared, and the exercise says find f prime of x using the definition of derivative. Easy, clear as day. the derivative of f, by definition, is the limit when h tends to 0 of f of x plus h minus f of x divided by h. We apply our function here. Only have the limit when h tends to 0 of x plus h squared minus x squared divided by 8. Okay. The series dividing here, this looks something weird, so let's expand this perfect square here and see what happens. Here we have the limit when h tends to 0 of x squared plus 2xh plus h squared and minus x squared. This gentleman and this gentleman have the common decency to cancel each other out. And what they have here is h multiplying two things, and it's dividing as well. So we can do this. Now, h with h, because it tends to 0, but it's not exactly 0, cancel each other out. So this is the limit when h tends to 0 of 2x plus h. Now, questions about the definition of derivative? No questions, good. That means that this weekend when I start correcting the exam, I will have to give full points to everybody. It's always good to have good news. Unless now number 3. Number 3 is the reason why I have told you several times that you definitely should derive perfectly in order to be able to do calculus. We have y equal arctangent of 1 over x. There are two ways to solve this. One of them is if you know what the derivative of the arctangent is, and another one is if you don't know what the derivative of an arctangent is. So first of all, we're going to cover the case in which we know what the derivative of this is. The derivative of the arctangent of u, of a function, is u prime over 1 plus u squared. And maybe you're thinking, but Germán, you told us the other day you didn't know this derivative. You lied to us. Yeah, kinda. I pretty much forget it all the time. So it's the exact same thing as if I didn't know it to begin with. So by applying this, the derivative of u, in our case 1 over x, is minus 1 over x squared. And here, 1 plus u, which is the thing right here. And now we just figure out a way to put it a bit more nicely. This x squared comes to the denominator, and this becomes x squared plus 1 over x squared times x squared, 1. That's one way. Now the other way. Imagine that we, for whatever reason, forget that the tangent of this is, well, we don't know the derivative, so I'm going to delete it right now. You forgot the minus sign, so your answer would be wrong. Your answer will probably be incomplete. So you are most likely to not get full points, but if you have form here, you will probably be all right. So if we don't know what the derivative of the arctangent is, we apply our other tool, which is implicit derivation. I told you once, you will never get tired of seeing this, and it's right. One does not simply get tired of implicit derivation. So what we have here is, first of all, the tangent of y is 1 over x, which is the definition of the arctangent. And now we can derivate. We derivate with respect to x, and we have 1 over cosine square of y times y prime equal, we derivative with respect to x, minus 1 over x squared. We move this here multiplying, and so y prime would be cosine square of y divided by x squared, and with this minus sign. Fair enough. And now, what's the cosine of y? In order to do that, we go to our goniometric circle. This is the tangent. This is the sine. This is the cosine. We know the tangent, we need a cosine. What do we do? I'm waiting for you guys. Okay, you got me. This is not the form that we want to use here. So I'm going to fell to the ground. I'm going to rewrite it this way. And here I'm going to do the same. I divide by this. Now, what's this? Tangent of y is 1 over x. Tangent the square of y is 1 over x squared. So all this thing is equal to minus 1 over 1 plus 1 over x squared times x squared. One problem, two ways. Both are valid. The result, such like that. And there is a third method to solve this, which is what explains this thing right here. All right. But I'm definitely not going to get into that. So we have number 3A. At this point, we're almost halfway through the exam. We are pretty convinced that our grade will be big enough, at least for a 3. We almost have the 3 there. We are touching it with the tips of our fingers. But first of all, we have to continue. We have to go on. We have to derivate y equal x logarithm of x. If somebody gets this one wrong, I will get very angry in the next tutorial. So please don't. This is a product of functions. So the derivative of this is the derivative of the first times the second without derivative plus the first underivated times the derivative of the second. Fixed, done, ready. One line, 15 seconds. If you write in paper instead of in a whiteboard, it will probably take you less time. So everybody has it clear with x logarithm of x? Good. I like your spirit. Now, going on. We have y equal sine square of x. For those of you who may be having issues with this notation, this is sine x times sine x. So it's a product of two functions. What's the derivative? Derivative of the first times the second underivated, cosine x, sine x, plus first underivated, derivative of the second, sine x, cosine x. And if you were paying attention when we would talk about trigonometrics, this is nothing else than the sine of 2x. Although both solutions are fine. Good, so moving on. We have solved 3 full exercises. We are feeling the exam. We are starting to feel good. The excitement is taking over the anxiety of the exam. And this one we have passed. Yes, it is. We have passed the halfway. At this point, we are starting to think if this exam is too easy or if we may be something wrong to find it this intuitive. So let's go. Yes, Mahmoud, that's correct. So this is a box. My box is amazing. A thin box with a square bottom. So we're going to call the side of the base x and the height y. And we know that the volume of this cube is 4. So first piece of data we have, the volume of the cube is 4. Second, we want to minimize the area. First of all, volume. And second of all, we want to minimize the area, the surface. What's the surface? The surface is the area of the square of the base plus the area of the 4 sides, because the box has no lid. So 4 times base times height, x, y. Now these functions depend on 2 variables. So we're going to change them so they depend on 1. We have x squared and y, so we can put y in terms of x. And we put it here. So the surface is x squared plus 4x4 divided x squared. This thing cancels here, x squared plus 16 over x. This is the function we want to minimize. And how do we minimize function that depends on one variable? By using the first derivative. The derivative of this, sum of two functions. The first summa is 2x, and the first one is 16 times 1 over x. So this plus is a minus. No problem up to here. And now we want to find a critical point, so we put the first derivative equal to 0. This is equivalent. We're going to multiply everything by x squared. To x cubed minus 16 equals 0. For now, we can divide by 2, and we have x cubed equal 8, which means x equal 2. Now, this is the base. What's the height? The height is y, which is equal to 4 over x squared. We put our x here. And here we are. Our optimal dimensions are 2 and 1. But how do I know that the surface is minimal? Well, in order to see whether the surface is minimal or maximal, I need to use the sign of the second derivative. Second derivative is the derivative with respect to x of this thing right here, 2 minus 16 times minus 2 over x cubed. This is 2 plus 32 over x cubed. And this is greater than 0. Always. This is positive. This is positive. But wait, sorry, you can't see this. I just said that this point gives us minimal area. However, what's the question? The question is, what should the height be? The height should be 1. The height of the box is 1. 1 meter. One decimeter, 1 over 10 meters. How do we know that this is 1 decimeter and not 1 meter or 1 kilometer? Well, a cubic meter holds 1,000 liters. A cubic decimeter holds 1 liter. Real life. If you answer the height of the box is 1, it's still good. It's still good though. Now, questions about minimizing the base of this box. Remember key steps? We know the volume, we know the area. Okay. So moving on, we have solved 4 exercises correctly. We are incredibly pumped. We are motivating. We can feel the fantastic day opening upon us. And it's already been 25 minutes, so we are pretty good to go. Now there's only 2 more exercises, and we may go home and walk away from the room with the total security that we have a 5 in this exam. So speaking of 5s, let's solve exercise number 5, which is limits. So the idea of these limits is evaluate them or say why it doesn't exist. Now, how do we solve this? Cosine is continuous and limit is continuous. So what we are going to do here is this step. We move the limit inside. What's this? This limit is 0. So all this thing is the cosine of 0, which is equal to 1. Beautiful, fast, quick, efficient, just the way I like them. Now, for the second one, I have been told by the colleague who is correcting the exams in Swedish that a lot of Swedish students have struggled with this, but there is really nothing to struggle about here. This limit is the cosine of e squared, which is a real number. And finally, don't we need to know which number that is? It's this number. This number. Cosine of e squared is a perfectly defined number. If you want to look at it from a numerical standpoint, this is something between 6 and 9. So you can say that is close to 2 pi, so maybe this number is between 0 and 1, but it doesn't really matter. This is the value of the limit. Now, our final suspect is a quotient of polynomials. You have 2 ways to solve this. The first one is remembering the rule of degrees. The largest degree rules, all the rest don't matter. And we immediately know that this limit is 3. If you want to do it to impress your examiner, you divide by the term with the largest degree. And you have 3 plus 2 over x plus 1 over x cubed over 1 minus 7 over x squared minus 1 over x cubed. And so what we have here, the quotient of 3 plus 0 divided by 1 minus 0 and minus 0, because all these terms that are dividing here are divided by infinity, so they become 0. So this limit is 3. Now, questions about the limits. One. Where is the 1? In A, I move the limit to inside the cosine. Okay, this step that I'm showing you here, it's usually hidden. Every time you solve a limit, you are implicitly doing this thing right here. You are allowed to do it as long as the function you are exchanging with the limit is continuous. So in this case, the cosine is continuous in the area that we are talking about. So you can exchange the cosine and the limit. Later on, in one of the last topics of the course, we will see when exactly we can do this with derivatives and integrals, because that's a very interesting topic as well. And there is a powerful result called Lebesgue's dominated convergence that allows you to exchange an integral, a limit, and a sum, because all three are continuous operators. So if this is continuous, you can put the limit inside, and that's how you evaluate it. If you want to look at this step, when you go to infinity, this becomes very small. And so in the end, you're working with the cosine of something very small. It's the same. You are really not required to know this step. You should, but you're not required to. Yeah. So moving on, we have solved 5 exercises. We are accelerated. Our math skills are being put into test, and we are destroying the test. We are having a breeze. All the hours watching the tutorials all over and over again are finally giving us fruits, and we proceed to about exercise number 6, and then we can go home. We have no initial conditions in this equation, so we only have to find the general solution to it. In order to find the general solution, we have 3 steps. The first step is if we say that we have a solution in the form y is e in power lambda t, we can build the characteristic equation. And we have our characteristic equation is lambda squared plus 3 lambda plus 2 equals 0. Second step, eigenvalues, which is the same as to say roots of this. So lambda is minus 3 plus minus the square root of theta squared, which is 9, minus 8 divided by 2. This is minus 3 plus minus 1 over 2. And so lambda is either minus 2 or minus 1. And how do we test that these roots are true? The product of both is 2, and the sum is minus this coefficient here, so they are right. Third step, we use the eigenvalues to build a general solution. If the eigenvalues are both real, a general solution has the form A, E in power the first eigenvalue times t, plus B, E in power second eigenvalue times t. Three points. There's a lot of dust here. So, questions? All right. So if you have no questions, I guess this is clear as day. I'm going to hope it is. Now, instead of answering the questions in the exam, I'm going to ask one for you guys. Now that you have seen the solutions, how do you think you did? Okay, so people who took TEN1 last week, how did you do? How was it? Are you pretty happy with what you got? Are you thinking of retaking the exam? Are you scared because you are not entirely sure where you got 2 points, where you got 1, and if or when the case will accompany? I want to hear your thoughts about the exam. Could have been better. Good. Good. I'm happy you like my explanations, because I was reading the solutions you had on Canvas, and it's always much better to have someone do the exam for you instead. This is something we used to do when I was doing my bachelor's back in Spain. The professor of single variable calculus would always take 1, 2, and sometimes more hours to cover the exam and help us beyond the corrections, because once you get a grade, you'll be, yeah, you got a 3, but why, when, where am I missing? What's the correct way of doing? That's something that you're not going to get if you get a PDF sheet with the solutions. You have to be there and involve yourself. So hopefully all of you that haven't answered will be having good grades. For now, I'm going to pick up a cup of coffee, and I will see you in 5 minutes, which means now we have some time left. So if you have questions regarding exercises that you have been doing or practicing with, or maybe my Sharpie just decided to end its life, so I'm going to pick it up. But suggestions, questions, and everything in the chat. Floor likes pen, indeed. No questions? Okay, then I will talk. Yeah. So I think you will see this in the lecture of Monday, but yesterday myself and one student figured out a really interesting way to introduce this. So I'm going to do it anyway. Then I will show you a super cool example of this thing, and then we can go home and enjoy the day because it's +11, the sun is shining, and we definitely shouldn't be trapped at home listening to a bearded guy with a bun talking about math. So let's go. I am going to assume for this that you pay a lot of attention when we were talking about Riemann sums. Although I told you I didn't like them, that doesn't mean they're not important. Imagine that we have this function, y equals f of x. And we want to roll it around the x-axis. Okay, so this is a phantom line. More bars here. If we spin it, I'm going to build here your Riemann sums, your Riemann rectangles. And then we spin them. This diagram is going to look terrible in the video. My apologies in advance. And we do that. And here what we are doing is we don't really spin the curve. We spin all those Riemann triangles. Those Riemann rectangles. Those Riemann rectangles, they define cylinders. We can call it C1, C2, C3, boom, boom, boom. So the volume of revolution is the sum of all this, of the volume of the cylinders. What's the volume of a cylinder? The volume of a cylinder is surface of the base times height. The height here is 1/n because we do our partition with, we build n parts and then we revolve our Riemann rectangles. Now the height is 1/n. The surface of the base is pi r squared, right? Good. Now what's r? What's the radius? What's the definition of y? Oh. Y is the curve f of x. Now, what's the radius of these Riemann disks? The radius of these Riemann disks is no other than the height of the rectangles. Right? So we have the sum of all these cylinders. Now, if only we had a tool to take this limit and sum an infinite amount of ridiculously flat cylinders. There you go. This is A, this is B. we work in an integral AB. This is no other than this thing right here. And you'll probably get tired of seeing this, and you will look at the book and find this formula, but this is why. This is in the same way that the area under a curve is defined by the Riemann rectangles. The volume of the revolution solid is defined by the areas of the Riemann cylinders. I don't know if they're called Riemann cylinders. Maybe you will look that up in Google and won't find it. I don't know. But this is how. If I wanted to revolve the function around the y-axis, let's see what happens. We have another function f of x, and we want to revolve it around this axis. So instead of building our Riemann rectangles like this, we have to build them in the other direction. So we can treat this as x equal g of y. We treat x as a function of y. We build our Riemann rectangles. And then we spin them. Rectangle 1, rectangle 2, rectangle 3, and like that. And so since our function is a function of y, what we have here is that the surface of the base of these cylinders is not pi fxy squared. It's pi times this new radius, which is g of y. So if you want to do a revolution along the y-axis, you change the order of the variables. You twist the function around, and then you get the vertical base instead of the horizontal base. Now, is gy the same thing as f inverse of x? Yes, it is. Yes, it is. So I'm going to write it here. The idea is you have to treat the variable whose axis you revolve around as the variable, and the other one as the function. And that's how you manage to solve this. Now I'm going to show you a super cool example. Little reminder here, this is pi times the integral in the interval of f of x squared differential of x. And what I'm going to show you now, the volume of a sphere. So imagine that we have a function like this. From minus r to r, we have a half circle with radius r. Right? This is y equal square root r squared minus x squared. And we want to revolve it around the x-axis. What we form here? A sphere. How do we pose this? We have to find this sum of disks. How do we do it? We see the volume as pi times the sum of all these radius squared. In our case, our interval is from minus r to r. Good. You use this integration to find the volume of the skate park pit at your old high school. Nice. That's a very nice application. However, there's one thing you have to remember, and it's that skate park ramps are not parts of a circle. Skate park ramps are parts of a curve called cycloid, which is known as the curve with the fastest descent. We will probably have time to talk about the cycloid later on. For now, we're going to solve this, and one way to do it, there may be others, but one way to do it is considering the following substitution: x equal cosine of u. If we do like that, sorry, sine of u. If we do like that, sorry, the limits of integration are were never my strong. So and now what is interesting here, we put an r here. The change is x equal r sine of u. And this is r cosine of u. How? This is r square root of r squared minus r squared sine squared. By using cosine squared plus sine squared equals 1, this is a square root of r squared cosine squared. So we take the square root of everything and we have this. Sorry. I have to do a small fix here. If x equals to r, it means the sine of u is 1. So x is no other than pi over, sorry. And if x is minus r, means the sine of u is minus 1, which means x equal minus pi. Okay? Now it makes sense. So x equals minus r means the sine is minus 1. So the angle is minus pi or pi. We can see it the way we want. We will use this and see what happens. Now, our integral is from minus pi to 0 of r cosine u. And what's the differential of x? The differential of x is r cosine u differential of u, right? We derivate this, and we get the constant. The sine becomes cosine, since we're derivating towards u, du. Fair enough. Now I'm going to use the only two trigonometric identities that I know to figure this out. And those are cosine squared x plus sine squared x equals 1, and cosine squared x minus sine squared x equals cosine of the double angle. if you sum these equations, you get 2 cosine square of x is 1 plus cosine of the double angle. And so cosine square of x is 1 plus cosine of the double angle divided by 2. And this is what you're going to use. Will you ever need more trigonometric identities? Maybe, but these two are very useful. So this is pi integral from minus pi to 0 of r squared 1/2 plus cosine of 2u divided by 2 differential of u. We separate these two integrals and we are almost there. Let's see what happens. This is pi integral between minus pi and 0 of 1/2 differential of u. Plus pi integral from minus pi to 0 of cosine, r squared cosine of 2u divided by 2 differential of u. Now, you may be tempted to solve this integral immediately, but we have to return the substitution. And so this is equal to pi integral from minus r to r this is pi u divided by 2 between minus pi and 0. Okay? Can't see it. It's out of the pen. Let me fix that. No. This is pi u halves of minus pi and 0 plus pi r squared divided by 4 sine of 2u between minus pi and 0. Okay, this looks kind of good, right? Now we obviously have to turn down the change of variables, so let's see. Let's see how we avoid that. This is the inverse change. Now the sine of 2u is 2 sine u cosine u. This is I lost the whiteboard. And so what we have here is that thing right there. This is sine square. If you multiply everything by r, you have to, sorry, by n square, we have 2r sine u, and in the square root, so close. This is equal to 2r sine u square root r square minus r square sine square u. Now, why is this change interesting? Because this is x, and this is x squared. And I've run out of space, so I have to borrow it from somewhere. So here what we have, this is pi. Arc sine of 1, 0. Arc sine of 1, 0, no, arc sine of 1 is pi over 2. So I've actually messed up the limits of integration. It goes from minus pi halves to pi halves. And so when we do this, this is pi over 2, arc sine of 1 is pi halves minus arc sine of minus 1, which is minus pi halves. Plus here, pi r squared over 4. That multiplies 2x square root r squared minus x squared between minus r and r. Let's see what's going on here. This is pi squared over 4. It probably shouldn't, but it is. Let's see how we attack it. Plus pi r squared over 4. And here we have this thing. Is 0 anyways. It is 0 anyways. Sine of pi, sine of minus pi. So all this thing cancels, which means I have forgotten to multiply by something here. Huh. You guys are going to kill me, but there's a mistake somewhere. because this is 2r 0 plus 2r 0, which is not working. Okay, this happens sometimes. So I'm going to start over. You may be wondering, will this happen to us? Yes, it will. It definitely will. So let's see again how we abort this function. This integral here. There was probably a mistake with the integration margins from the very beginning. So we'll do it again. But this time I'm going to use the cosine because I can, mostly. And here, the square root of r squared minus x squared is the square root of r squared minus r squared cosine squared. And this is r sine of u, which is good. Now, if x is minus r, this means cosine of u is minus 1. So u is pi. If x is r, this means cosine of u is 1. So u is 0. And finally, differential of x is minus r sine of u, differential of u. This pen wants something, but it doesn't know how to speak English, so it just has to tell me the song of its people. So let's rewrite this integral. We rewrite it as pi integral from minus r pi to 0 of r sine of u minus r sine of u, differential of u. So this is with this minus, I'm going to swap the limits of integration. Now I need to use the magic trigonometric identities again. Now, Joe, you can produce every single trigonometric identity from these two. And so we do this equation minus this equation, and we get 2 sine squared is 1 minus cosine of the double angle. So this is pi r squared integral from 0 to pi of 1 minus cosine of 2u divided by 2 differential of u. Now, let's see what happens here. We separate the integrals. We have pi r squared times the integral from 0 to pi 1/2 differential of u. This is a constant times the constant times the length of the interval. I made the biggest mistake ever, and no one has told me. Nobody has told me. 9 people there with me, and nobody has told me that the function is squared. God damn it, guys. I need you with an eye on the details. Now we're talking. So this integral from pi to 0 of r squared sine square of u with pi multiplying here times differential of u, so with a minus, the r cube is here, and the sine cube is here, differential of u. What was the difficulty we were finding out there? No r cube. Problems. So now, sine cube of u is sine square of u times sine of u, which is fair enough. How do we operate this? This is sine of u minus sine of u cosine square of u. Let's see if this takes us in everywhere. Doesn't look like it. So this is sine of u times 1 minus cosine of 2u divided by 2. This is sine of u over 2 minus sine of u cosine 2u divided by 2. And I lost it to the very tight margins of this white body. So sine u over 2 minus that thing right there. But now, let's notice one more thing. I'm going to play with this cosine and make it dance to my rhythm. Cosine of 2u is cosine square of u minus sine square of u. Very good, huh? This will be good to consider later, maybe. Minus sine plus, perfect. So let's plug this into the equation and see what happens. Minus, I'm going to use this minus sign to swap the limits of integration again. From 0 to pi of r cube sine u divided by 2 differential of u minus pi r cube. This thing right here. Okay. Now, this one is immediate. This is minus pi r squared divided by 2 cosine of u between 0 and pi. Now, cosine of pi minus 1. So this is pi r cube divided by u, the minus with this minus becomes plus, minus with this minus becomes a plus, pi r3 divided by 2 cosine of 0, 1. So this equation here is pi r3. So I'm going to delete everything until here, and we'll go on. Is this visible on the screen? Perfect. This is correct. This is correct. Two comes here. Now, how would you guys solve this? You can take the 1/2 out of the integral. Yes, yes, why not? Remember here that we are using the change x is r cosine of u. Cosine of 2u as another trigonometric identity. Let's do it. But the problem with using another trigonometric identity is that here we split this as cosine squared minus sine squared, and in the end we get an integral that cancels with this one, and we get this equation back. So actually I'm going to use another tool, which you will see soon, I think, which is called integration by parts. What I want to do here is to express this function in terms of simpler trigonometric functions. In our case, we have to pick up two variables, one which is b, namely cosine of 2u, and this thing right here. And so when we swap them, we have the differential of v is minus 2 sine of 2u differential of u, and w is minus cosine of u. So if we integrate it by parts, I'm going to solve this equation separately. That is dw minus, with this minus becomes a plus, the integral of this thing right here. This doesn't become a plus, this is actually a minus. It doesn't look like we have achieved much, but we can use integration by parts again. And here I call V I call it that way. Yeah. Differential of W, cosine of U, differential of U. So W is the sine of U, and differential of B is 4 cosine of 2U. Usually when you integrate by parts twice, there is a chance that the integral cancels, but this 4 is going to fix it for us. So we have minus cosine U cosine of 2U from 0 to pi minus 2 sine U sine 2U between 0 and pi, and minus with this minus is a plus. This thing right here, 4 cosine of 2U sine of U differential of U. Okay? So I'm going to erase the whiteboard again because I'm absolutely in need of space. And I'm going to write it down. I'm going to write this down. This is 1/2 of all of this. Between 0 and pi plus integral from 0 to pi of 4 cosine to U sine U differential of U. Why do I put this apart? Because this integral is 4 times this thing. We integrate by parts twice, and we've actually figured out something. So we move this thing here and all this thing to the other side. And what we have is that 3 integral between 0 and pi of sine U cosine 2U differential of U. Of course, we divide by 1/2 because we can. Is cosine of U cosine of 2U plus 2 sine U sine 2U from 0 to pi. Since we don't want these 3, we put it here, and there we go. Now, we can replace all this equation here, but first I'm going to solve it. We evaluate this in pi. In pi, the cosine of pi is -1. The cosine of 2 pi is 1. So this is -1 plus 2 sine of pi, which is 0, times sine of 2 pi, which is 0 as well. and minus. Now we evaluate in 0, 1, 1, minus 1. And when we evaluate in 0, sine is 0, sine of the double angle is 0 as well. So all this equation is equal to minus 2/3. Now, would you look at that? This castle is minus 2/3. Now we can put it. Now we can put it there. Is it visible? No, it's not. However, incredibly small detail. Technical, small, hidden, there. So now we're going to erase this part of the whiteboard. And this full integral is pi r3 minus pi r3 times minus 2/3 times this 1/2 here. The 2 cancels with the 2, the minus cancels with the minus. You sum everything up. Boom. We did it, boys. We did it. It probably took too long. If my first analysis professor would see this, he would probably be mad. But still, we got there. We got there, guys. So yeah, now the volume of a sphere is 4/3 of pi r squared, whether we want it or not. Now, there is actually another way to arrive there. If we imagine this as a function of the radius, you will notice something. If you do the indefinite integral of this, but now what's going on here? What is really going on here is that when you treat this as a function of r, you're only moving over one quadrant of the circle, because when you go on the other quadrant, the radius changes sign. And obviously, if you were to integrate in all this space, plus, minus, you will get 0. So you want to go with all quadrants. and you get that the volume so it makes sense. It makes sense from a geometrical standpoint. It was a bit easier, yes, but there are some very technical details that you have to consider here, and it's the way you run around the radius, because that's not always easy to work with. And actually, you may be thinking, hey, this is not true. Indeed, I lied to you. Why have I lied to you? Because this is a surface in 2 dimensions. How many dimensions does a sphere have? 3, correct. The volume of the sphere is 4/3 of pi r cubed. But what's the surface of a sphere? The surface of a sphere is 4 maximum circles. What happens if you derivate this? The derivative of a volume is a surface. The integral of a surface is a volume. Actually, I can prove that to you. I'm going to write this down. The integral of a line surface, exactly. The integral of a body in n dimensions belongs to a space with n+1 dimensions. A question about integration. Let's do it like this. Next session, I think we have integration by parts, and we have other tools of integration and all that. So we are going to call this a day. Write your question down, and Monday at 10:15 a.m. after we present the exercises, we will see it first thing in the morning, and then we'll begin with exercise. For now, I want to call this a day because it's Friday. It's 3:10. The sun is shining, and I overall want you to have a nice day. So that'll be it. Who's presenting? I don't know. Who's presenting? Mahmoud wants to present. Gaviria doesn't want to present. Let's keep the mystery. Let's keep the mystery. Actually, have a list with people who haven't presented yet. So we will do something in that direction. But for now, what we are going to do is close this meeting, call this a day, and I will see you guys on Monday morning. Don't miss it.